Okay, make sure you write your name on the chat, please, for attendance purposes. All right, looks like a lot of you are here already. Make sure I am where I need to be. I'm going to get started. Okay, last time we were looking at electron configurations, I believe. All right. Let me go to that PowerPoint and we'll go there. Okay. Right, I think I've recorded every one of you, but still make sure that you put your name on the chat so I'll know you're here. Okay, so when you look at electron configuration, you want to make sure that, okay, I downloaded it. Where is this thing? There it is. Okay, that's not the other one. There we go. Okay. I'm saying we're looking at putting in the electrons as they are going in, basically the lowest energy closest to the nucleus, the higher energy farthest away from the nucleus. So as we are putting in the electrons, you always put in the lower energy first. There are a couple exceptions here and there, but mainly you put the energy, the electrons in the lowest energy orbitals first, like it is written here on this diagram. And the reason that you have 3 little boxes and 5 little boxes and 7 little boxes, it's because different type of orbitals can hold a different number. And I'm going to write that down here so you'll remember. Okay, so every single orbital okay, so and I don't know who it is. Okay. All right, so like I said, every orbital holds 2 electrons. Now, depending on the type of orbital, on the level, the sublevel, I should say, because electron sublevels are either S, which can hold 2 electrons maximum. So that means it has 1 orbital only. P's can hold 6 electrons maximum. Which means that we have 3 orbitals. the Ds can hold 10 electrons maximum. Which means that we have 5 orbitals. And the last one is the Fs can hold 14 electrons maximum. Maximum, I missed it. Okay. And that means we can have a total of 7 orbitals. So this may be asked of you at some point. So just remember these, okay? These numbers are easy to remember because the region of the periodic table that holds them, S, P, and D, if you count the number of columns, they're exactly 2, 4, 2, 6, 10, and 14. Okay, so let's keep going. Okay, so and we're just going to leave this written thing up there so you can remember. All right, so I'm just going to move it. Mom can't move it, but there are rules that govern the way that electrons are put in orbitals. And there are Pauli's exclusion principle, which states that no 2 electrons in the same atom can have the same set of quantum numbers. What is a quantum number? A quantum number is a numerical description of the electron's position in an atom. And there are 4 quantum numbers for each electron, but no 2 can have the same 4. So even if they're in the same orbital, same type of orbital, so in other words, they're in the S, they're in 1, but there's one that goes up, one that goes down. And the reason that is this is called the spin quantum number. So the spin is different, okay? So that's what that means. So every time that you see, this is what is known as an orbital diagram that you're seeing here. Oh, sorry, and I know you can't see what I'm saying because I have not yet hit the spotlight. Okay, yeah, right here, this area right here, right? If you had one going up, one going up, that would be incorrect. Both of them were going up or both of them were going down because no 2 electrons can have the same set of 4. That being said, like I said, the 4 quantum numbers are a way to describe the electrons mathematically in each electron in an atom mathematically. And it's a little complicated, but quantum numbers, pretty much, if you know what you're talking about, then you know which electron they're talking about by just the numbers they give you. Basically, that's how that works. All right, so in this one, this is the same little diagram that was at the beginning. This is just an energy loading the diagram. So this is the next rule. It's known as the Aufbau principle, which states that every electron will occupy the lowest orbital that can hold it first. Okay, so every electron will occupy the lowest energy orbital that can receive it. So that means that we don't start loading here. We start loading here. And then if we have leftovers, we go here. And we've got leftovers, we go there, then there, then there, then there, then there, like that, in that order. But we don't just go from here to here and then over here. No, that's just crazy. Okay, that's all it means. Next, the question, Hund's rule. Hund's rule states that orbitals of equal energy are each occupied by one electron before any orbital is occupied by a second electron. So based on that, we have an orbital diagram on the right and an orbital diagram on the left. Which one of those is correct? Right or left?
Right.
Correct. That is the correct one. The other one is incorrect because you loaded it before you had one in here. And that's what it's saying. So that's what you need to know. All right, so let's look at this. So oxygen, orbital diagram would be, remember, these are to put all 8 electrons of oxygen in there. So we got the first 2 in the 1s, then we move on to the 2s, and we put another 2 there. Because based on these rules right here, right? Also, we're looking at that. And then we have the p's. And the electrons on the p orbitals, and by the way, you write, every time that you see a p, you're going to have 3 little boxes or 3 little lines. I use lines because it's faster. But you're not going to always have an electron in it. That's because the p orbitals exist as a whole. In other words, you have p's, you have all 3. And you have 1, 2 more. There's 3 more. And the last one goes there. So that's how that works. And then the last thing to do is the orbital configuration. That's the orbital diagram. Now we have the electron configuration, which we just write. It's the same thing. This is one type of notation known as an orbital diagram. This is the other. This one is the one you'll be more familiar with. Okay, here's another one. Longhand for sulfur would be 1s, 2, based on those rules down there. 2s2 because it's full. 3s2, no 3s2, right? It would be 2p6. See, the 3s doesn't come yet, but 2p does. Then we have 3s2. And then we have 3p6, but it's not full, so we can't say 6. We have to actually count how many electrons. So it's 16, there you go. 4 in the green ones, right? And 6 in the yellow ones. And remember something that you know about each one of these configurations. When you look at these, I'm going to show you. This number right here tells you which period you're in, and you're on period 3, which means that the maximum level of electrons that you have is the 3rd level. And this other number, and let me make it in red, right here, when you add them together, gives you the group number. That's 6A. Right? See? That gives you the column. Just remember that, okay? All right, so mouse, let's go. And the other thing that you can do is add them up. If you're not sure that you did it right, you can always add the electrons up, and they should add up to the number that you're looking to put in. And these yellow ones are your valence electrons. That's why the group number is 6A. All right, and the other ones are your core. And remember, there is another shorthand where you put the core as a noble gas. It has to be a noble gas, cannot be anything else. So the noble gas, how do we know which noble gas? So if you look at the periodic table where sulfur is located, put your finger on it, go up 1 to oxygen, and then go all the way across to neon. And there's your noble gas. It's the one before it, okay? It can never be the one after it. It has to be the one before. And then you simply bring down or rewrite the rest of it, which is your valence electrons right here on this side. Okay, so that's basically the whole thing. Let's keep going. All right, so this, hold on, let me clear all this stuff. I am going to have to clear this part. So let me clear all of it. So now you know that you had all that stuff to do. Oops, not stop share. That's not what I meant to do. Sorry. I'm going to reshare. That is so not what I meant to do. I meant to clear. And I put my finger on it, but it went down. Okay, there we go. All right, so if you are following this like reading a book, right? If you look at each one of these, you are going to write. You always read a book by following the line, right? And then going back down, reading the next line. Notice how I'm trying to make it as straight as possible. It's not going to be straight. Then the next one, you read that line. Oops, that line was supposed to be straight. And then this line, it's hard to do it because I have to stop in the middle of it so I can go all the way across. So you can see how each one of these is going to fall in there first. Now this one, you have to go detour over here, then come back over here and keep going there and then finish. Same with this one. This one goes here, goes down here, comes back around to the 7, to the 6Ds. And then there's also the 7Ps, which they're not there because at the time this was made, we did not know about those yet, but we do now. So there you go. So that's how you would do it. So any element that you choose, you're going to have to do it like that. So let's say we don't even know which element this is, but let's try to do the electron configuration for this guy right here. Okay. So what you would do is you would write down 1s2. That's these two, right? Then you would do 2s2 because these two right here are taken, and then 2p6. And then 3s2. All of these, 3p6. 4s2. 3d10. 4p4. Oh, 4p6, sorry. 4p6. 5s2. See how it just follows directly? 4d10. And this last one would be 5p2 because we are on 1, 2. And this is where we want it to go. You see that? And we don't even know who that is, but I can tell you who it is. It is 10. That is 10. Has 50 electrons total. So if you were to add all the superscripts, these superscripts right here, it should give you 50. So you want to add them, go ahead. It's 10, 20, 30, 40, 50. Yep, that is exactly 50. All right, so that's how you do the electron configuration. Now, as far as the orbital diagram, that would take me a lot longer to do, so we're not doing that one. But the orbital diagram basically is the same thing, it's just with lines or with arrows, okay? That's all it is. It's nothing different than you've already done. All right, and that's your S, P, D, and F. And why do we have N minus 1 and F minus and N minus 2? Well, since we are in, oops, sorry, I forgot to put my annotation. Okay, there we go. Since we are in this group, right? You notice this is 4, but the coefficient for that D is not 4, it's 3. Therefore, D is N minus 1. And then here with the 6, okay, right here, We are in 6s, but this is n minus 2. So when we come back down, you notice it's 4. Okay, so n is 6 minus 2 is 4. And then go back up. And then, of course, now you follow the n minus 1, which is right here, right? And then, of course, the n, which is p, which is all of these are n's, right? These two. These are n minus 1 and n minus 2. So basically, wherever line you're on, that's how it's following. Now, you notice there are no D's on the third level. And there are no F's until the 6th. Okay, so remember that too. All right, let's keep going. All right, here's one example, hydrogen. Very simply, 1s1. But what does all this mean? That means we're on the first period, on the s block, or we have an s orbital, and there's one electron in it, which puts us on the first column of the s block. And these are, the blocks in here are color coordinated, except for the F's, which are not on there, but there they are. Now, if you have a shortcut configuration, and look, this is the reason why we go from 6. See, this makes more sense when you see it like this, because periodic table is not cut up. So 6, you got the n minus 2, which is 4, the n minus 1, which is 5, and then the n again. You see that? So that would be 6s2, 4f14, 5d10, 6p6 on that one column. All right, so look what it says. Go up one row and over to the noble gas. Okay? And then on the next row, fill the number of electrons in each sublevel. So following those rules, let's do some practice. Okay. Not working. There we go. All right, so let's do him. Germanium. All right, so go up one row from germanium over to the noble gas, which would be right there. Yes? All right, what's next? We write down the noble gas as the core. Okay, and then after that, we still got to get to germanium, so we need to say 4s2, then 3d10, and then 4p2. And there you go. That's the shorthand configuration for germanium. All right. Now, there's another thing about stability, and this is why we have exceptions. One of them being that if you have a full energy level, completely full, then you're at the most stable. That's why the noble gases don't react. It's because they are at the full energy level of stability, which is right at the end of the periodic table right here. Now, the other one is a full sublevel. So the full S, the full P, well, not the P because that's a full level. The full D and the full F are more stable. The next one is a half full. Half full, well, you cannot be half full S. So, it's either full or 1. So we're talking about the P. I'm sorry, the P here, the D here, and the F here. So these are the most stable of the others. Okay, so if they're somewhere here, they're not as stable. They're somewhere here, they're not as stable. But if they're here in the middle, they're much more stable. And then the other one is no particular order. All right, so copper, you would expect this because copper, where it is argon, and then you got a 4s2 and a 3d9. Yeah, that would be correct, except this is one of our exceptions. And our exceptions actually put the one electron from S into the Ds. But look why. Now the Ds are full. You see that? And didn't we say that that was a much more stable than the D being 9? So that's why it's seeking stability. That's why copper doesn't completely rot, or not rot, but oxidize, I should say. Instead, that's why the Statue of Liberty is still there, right? It's because a part of it is copper, and it gains stability with a full D sublevel. Chromium is another exception. Look where chromium is. You would expect it as 4s2, 3d4, but instead, that S is going to move over to the Ds and give it half full status. A half full status is much more stable. Therefore, it changes its configuration just because of that. All right, so now let's do some practice real quick. All right, let me get my book, and we are going to now, I'm going to write down some electron configurations, and you're going to identify them. That's the first thing we're going to do. Okay. So I'm going to go to the board. No share. Whiteboard. And remember, I'm writing these with my fingers, so don't expect perfection here. It's not. All right. So this is the one. Anybody who wants to identify it? Who is that? Which element is this?
Helium.
I'm sorry?
Is it helium?
Helium? No. It's not. Why not? Okay, helium is its core. No, the element keeps going until 2p5. So where is 2p5 on the periodic table? Okay, look at your periodic table. And helium is the noble core gas. The noble gas core, sorry. And helium, and then we've got 2s2, so it is not beryllium because it still keeps going. And then we got 2p1, 2, 3, 4, 5. This is fluorine. You see? Remember, helium has 2 electrons. And then you got 2 more and 5 more, so that makes it 9. Isn't fluorine 9 electrons? Yes, it is. Also, another thing to note, fluorine is in period 2, group 7A. You see that? All of that's being told. All that information is contained in that one configuration. Okay, let me go another one. Okay, which element is this one?
Miss Vides, you can like run through this back again one more time because
I'm sorry?
it get a bit confusing.
I'm sorry, I couldn't understand what you said.
I asked if you can run through it back, like go over it one more time.
Okay, go over the top one, the bottom one?
The top one.
Okay. All right. So let me go back to the periodic table. That might help you. Okay. So not in this one in particular, but let's go back to a periodic table. Okay, this periodic table. How's that one? Okay, so we had helium, right? And helium, as we know, is over here, right? Oh, sorry. If it would draw, it would be nice. It's not letting me draw. Okay, new share. There we go. All right, there we go, share. Okay, so now you can see it, right? So helium is, sorry, right here. Ah, it's not letting me write. Why are you not letting me annotate? I have it ready. Okay, helium's right here, right? And then it said 2s2. So we still are counting these electrons because that's 2s and 1 and 2, right? And then we've got 2p5. So 2p, so this is still 2. Remember, this is all still the same line. So we got 2p1 right here, 2, 3, 4, and 5. And this is our target. And if you look at the periodic table, that's fluorine. And fluorine happens to have 9 electrons, yes? Because fluorine is element number 9. Okay, so it has 9 protons, 9 electrons. 2 are from the helium that we had written down.
I think I understand now.
You got it?
Yeah, I think so.
Okay, well, let's go back to the other one then. And let's go back to the other share, which I was doing, the whiteboard. Okay, share that. Okay, so now can you tell me which one that one is? So periodic table again. I mean, maybe I need to go get a periodic table myself. That might help a little bit more for everybody. Just get one real quick out of the, we have one on here. So I'll just go to that one in our modules. Probably nobody knows yet which one it is. Okay, well, where is argon? Look for argon.
In group 3, like across.
Right, so you found your periodic table.
Yes.
Found it on your periodic table, I mean.
Mm-hmm.
Hold on, let me find my periodic table that I wanted to bring up so that I can show you. Where is, there it is. Found it. All right, so now I'm going to share this one again. Okay. So once you see it, okay, we are looking at argon, right? We said argon 4s2. So argon, we need to locate it first, and I already located it, but I need to, there, this one right here, right? And then we have 4. This is 4, remember? These all have numbers. That's 1, that's 2, that's 3, that's 4, that's 5, 6, and 7, right? So we're looking at 4. This right here is the S area, right? Both of these. So 2 means here. You see that?
Yeah.
So that's how you can identify it.
Okay.
4s2. All right, now let me clear these. And I'm going to keep this one up, but I'm going to do the new share. Okay, so we're going back to the whiteboard. And you said this was calcium. All right, one way to check. How many electrons are there in argon?
18.
18, and we added 2 more. That gives us 20, no?
20. Yeah.
See, pretty cool. All right, let's do the next one. All right, this one is krypton. So you can be locating it. 5s2, 4d10, and 5p3. Okay, you should be able to identify that one based on what I showed you. Okay, let's go back to the periodic table to look at it. I have to get a new share again. Okay. All right, so we said krypton. So this time we have this guy. Oh, sorry, wrong one. Krypton right here. And then we said, again, 1, 2, 3, 4, 5, 6, 7, right? So 5s2, that would be these two. But it goes beyond that. Then it says 4d10, that's all of these guys. And then it says 5p3, no? Okay, so 1, this is 1, this is 2, this is 3. So this is our target right here, antimony. You see that? So far, so good? Yeah. All right, let's clear this one.
Yeah, sorry.
No, it's fine. And got a new share back into the board because I got another one for you. But we're first going to add up. Okay, so krypton has how many electrons?
36.
36. And then we're going to add 2. That's 38. Plus 10. It's 48. And 3 more. Is what?
51.
And what does it say for antimony?
It's 51.
Exactly. See? So we know that's what it is because of that. And we can actually make sure by doing the count. All right, one last one. We have argon. And we have 4s2 and 3d3. Okay, who is that?
It's chromium. Hold on.
4s2, 3d3.
3. It's vanadium.
Vanadium, that's right. And to check it, we have 18, right? Plus 2 is 20, and 3 more is 23. 23 electrons equals vanadium, yes? See? That's one way to check it. Now, another thing is if you're given an electron configuration like a long form or a short form, you should be able to identify them either way. And you should also be able to tell which the electron configuration of any element if they asked you. Like if they asked you, for example, to do the, let's see, the long form. Okay, so clear that. No, let's do it just a new one. Okay, so they want you to do the long form of aluminum. Okay, come here, you. Oh, not new share, no. Nope, I need to draw. There we go. Okay, so aluminum. Okay. Aluminum. It is 13 electrons. We know that. All right, so they want to do the long form. We start with the 1, S, 2. Remember, it's like reading a book. Go right across the periodic table. What's next? 2, right? And then S, 2. And across the middle area, there's nothing. And then you've got 2p. and there are 6 of them. We still haven't gotten to aluminum because aluminum is in the 3rd period. Then we got 3s2. And aluminum happens to be on that first column of the P's. So 3p1. That's the long form. And if you add them up, you will see there's exactly 13. Because 2 plus 2 is 4, 6 is 10, and 3 more is 13. Okay. The next thing is, what if they asked you for the short form? Well, again, look up, over, look up. So go straight up from aluminum, one row up, and then all the way across to the end of the periodic table. What you see there is neon, right? Neon is the noble gas, which is this. Then after that, you still have to get 2 aluminum, so it's 3s2 and 3p1. And we know that neon is 10 electrons, and that added 3 more. So there you go. Either way you look at it. What if they ask you to do the one thing we haven't done, which is the orbital diagram? The orbital diagram for aluminum, the whole thing. 1, that's 1s, 2s, 2p, and 2p has 3 of these, right? Because we know that all of that's 2p, and then you have 3s, and then you have 3p again. And 3p has 3 because remember, there are 3 orbitals in the p area. All right, so we got 1 electron here, 1 electron there. Remember, we're putting them in different, pointing the different way. Always fill that first and then come down. And then the 3s also full, but the 3p only has 1. And there you go. So that's the whole orbital diagram. And that's an S, by the way, it's just ugly, but that is the whole entire electron configuration, long form, short, and what is known as the orbital diagram. Nails are too long. It's starting to bother the writing. All right, the orbital diagram. So there you go. So you got all 3 notations. These are the 3 forms in which you can express electron configuration, okay? Got the long form, short form, and the orbital diagram. Your assignment has that too. I don't know if you've seen it, but it does. And it is exactly that. That's all it is. Just the same thing we just did, except there's one exception on there, so you got to be aware of it, okay? All right. That does it pretty much. We are finished. I will hopefully see you next time, but I can't promise. My vehicle is not my vehicle right now. My vehicle is in the shop still, and I don't trust this one to get all the way to Marshall and back as is right now, so I'm kind of trying to fix it. I already had one blowout. I don't need another one. All right, you guys take care. I'll talk to you later.
You too.
Bye-bye.